Okay, let's see what I got. Count the number of computer unlocking permutations, medium. Okay. You're given an integer array complexity length n. There are n locked computers in a room, labeled 0 to n minus 1. Okay. With each with its own unique password. The password of the computer I has complexity at I. The password for the computer labeled 0 is already decrypted and serves as the root. All computers must be locked using it or another previously unlocked computer. Following this information, you can decrypt the password for the computer I using the password for computer J, where J is any integer less than I with a lower complexity. I see. To decrypt the password for computer I, you must have already unlocked computer J, such that J is less than I, and complexity J is plus 1. Isn't that the same? You can decrypt the password for computer I using the password for computer J, where J is any integer less than I. Complexity lower than you decrypt the password for computer I, you must have already unlocked the computer. I really can't tell what the difference is here. Find the number of permutations 0, 1 through n minus 1 that represents valid order in which computers can be unlocked starting at computer 0 as the only initially unlocked one. Return the answer modulo 10 to the 9th plus 7. This answer going to start with 0, 1. I'm going to take a wild guess and say the answer starts with 1. One way. Okay. Complexity 1, 2, 3. Output 2. So I think maybe something like you go from 1, 2, 3 versus 1, 3, 2. Or, yeah, 0, 0, 2, 3, and 0, 1, 2 maybe. Those are the permutations. Unlock computer 0 with the root password. Unlock computer 1 with password of 0 since complexity of 0. Okay, so it's like you can go to a higher. Isn't this thing always going to be the lowest number? Maybe it can be higher complexity at the start. You have to go from a lower complexity to a higher complexity. We have to go from a complexity. You have to have a smaller complexity in order to go to another complexity value. So here there's 0 because you can never go to another 3. It's kind of like reverse of what I'm thinking, which would be like you need a higher complexity thing to unlock a lower complexity thing. But here you need a lower complexity thing to unlock a higher complexity thing. You decrypt password for computer I using password computer J, where J is less than I. J is any integer less than I. So it has to be something before it and smaller complexity. space before it. J is small complexity. You can decrypt. You must have already unlocked. To decrypt the password. Okay, I think maybe I'm going to do a couple test cases to verify that what I'm thinking about is correct. This return 0. I think anything with a decreasing value from your starting value, so like let's say 1, can you have complexity 0? Complexity must be positive. Must be at least 2 in the sequence. Okay, so I think if you have something decreasing complexity, I think that's going to give you 0. I think if you have something that is at all less than the initial value within that sequence, so like 3, 5, 7, 1, the 7 or the 1 here will never be part of it. So I think these are both zeros. Okay, yeah, and just like this is all this. If they have something that equals the starting value, then it's going to be 0. Alright, let's go ahead and do a small test case where where I can figure out what the answer should be. Let's say 3, 5, 4, 3, 5, 4. So here you can unlock 3 to 5 to 4, or 3, 4, 5. Do you always have to start beginning with 3? Why do you have to always start with the 3? Note that the password with computer with label 0 is decrypted, not the password, not the computer with the first position in the permutation. Not the computer with the first permission. Note the password for the computer with label 0. Valid order in which computer can be unlocked starting with the password computer 0 is decrypted. Not the computer with the first position in the permutation. What does that mean? Isn't 0 always going to be the first in the permutation? Unlock computers 0 to n-1, each with its own unique password. Password for computer I has complexity I. Password for computer labeled 0 is already decrypted and serves as the root. All others computer must be unlocked using it or previously unlocked computer falls. So 0 has to be the start of the permutation. But the password computer labeled 0 is decrypted. And not the computer with the first position in the permutation. That's what computer 0 is labeled. This is going to possibly bite me in the ass if I just kind of ignore it, maybe. I think I would want to just ignore it and assume that whatever idea I have about always starting with 0 is just true. And maybe this is just another way of phrasing it. Okay, anyways, 3, 5, 4. So yeah, this should be 2. 0, 1, 2. And then this is, yeah, I think this should be 2. Okay. Which is similar to 1, 2, 3. Alright, let's do something slightly more complicated. Okay, so here it should be 3. I mean, every order should work, to be honest. Starting with the 3. You get 3, 6, 5, 4, 3, 4, 5, 6, 3, 5, 6, 4. So that should give you 6. That's like 1 times 2 times 3 times 4. No, 1 times 2 times 3. 3 times 2 times 1. Something like that. 3 factorial. Okay. Interesting. Interesting. So what's the main what's the main deal here? So from any number, if there's ever a number that's smaller than the starting number, then the answer is going to be 0. So I'll do a quick sanity check. Impossible to sequence, permutate, if a computer has complexity less than or equal to the starting. So if the minimum of the complexity array is less than or equal to the start of the complexity array, return 0. Okay. But then when do you actually care? Because if the lowest one is the starting, then the lowest one can be treated as the j, index, where any other following thing can be used, or it can be used as the decrypting computer, or it can be used to decrypt a later index, I think. When is this ever not going to be like n factorial? What's going on here? Okay, I think I just want to see I guess if I just do some sort of random test case, it should be giving me something. Okay, that should give me 0. And then let's say it's going to be 1, 4, 5, 2, 5, 7, 11, 9. Okay. Here I'll say my default answer is going to be return n is equal to length of complexity and return like n minus 1 factorial. Factorial Python. Is there math.fact? math.fact, good for factorial. Okay. 1, 2, 3. Oh, I think I. Well, if the minimum is less than. Shoot, this is wrong. If the minimum of things after complexity at 0. Ugh, okay. If any, non-starting. I think I'll say low is equal to infinity for every index in range of complex 1 to n, where n is the length of complexity. If low is less than complexity at I, low equals complexity at I. And then if the low is less than or equal to starting. Yeah, capitalize. Oh, I said index. Whoops. Okay. Interesting. This should have been set to 0, no? Why did this not set it to 0? Or why didn't it return 0? Low. Low. Oh my god, I'm so bad. Good lord. Can't write a min function or min loop. I think I just need to do this mod and probably maybe create a better way of calculating factorial because this can be very large with n is 10 to the whatever. Oh, Jesus. Okay. I think, yeah. This might time out because this is too big calculation. Okay. So this was a lot of sugar coating or just a factorial calculation. I just don't understand what the hell, why. Don't understand why they make this so complicated when it's just literally every single permutation of the sequence. Everything's possible as long as you start with 0. So it's either possible or where it's straightforward factorial calculation, or it's impossible where it's just 0. Okay, this thing's just too large. N minus 1, where n is 10 to the 5th, the factorial, that's just too big. Like, that's a huge number and then fit into mod, but then the in-process calculation is probably just very slow. So I think maybe I want to separate it out. do a fast factorial calculation. Is there a factorial mod? Gorilla. Wow. Factorial. Iterative approach. Yeah, that's. There's something better here. I don't know about this. So yeah, you just combine it with the mod. Let me think. Okay, I think, okay, there's a couple ways I need to prove this. I think one is I need to do a better way of handling better way of handling this impossible case. I think I need to break early. So for every index in range 1 to n, rather than keep track of the low value, I just need to return 0 at the low value. If complexity at this index is less than complexity at 0, then I wonder if I kept track of the start. I don't know if this is any faster if you were to index into an array versus a variable. Here I just return 0. And then I guess I can maybe, I guess that's pretty darn fast. Here, otherwise I'm going to compute the factorial calculation. So the factorial calculation would be starting with 1 maybe. Okay, so the answer is equal to 1 for every oh, not n. Oh, I need to find n here. Guess I need to define mod here rather than before that. N is equal to length of complexity. For, let's say, I in range, I guess n minus 1. Is n minus 1? It's 1 to n plus 1. If n is 3, then it should be 1 to 3 because it's not inclusive. No, n is 3, that'd be 4. It should be 1 to 3, so it'd go 1 times 2. Okay. It should be something like answer equals answer times I percent mod, and then return answer. I guess I could probably start with answer being 1, but go from I from 2 to n. It's never going to actually want to multiply 1 times 1. Okay. 9. I wonder if it's faster to do the index part or if I wanted to truncate complexity. Like if I were to do something like this, for every value in complexity 1 on, if, yeah, I think that might be fine if value is less than or equal to start, turn 0. I don't know how this compares, to be honest. Compares okay-ish. It's the same. Because I maybe slightly prefer this look. I don't know. Answer in the range of 2 to n. What you could possibly do is do like a pre-compute of certain values. Pre-compute like factorial of one. What's the proper range here? Pre-compute factorial of, so 10 to the 5th, so maybe 10 to the 4th, 10 values. So 1 times 10 to the 4th, 2 times 10 to the 4th, 3 times 10 to the 4th, 4 times 10 to the 4th. At that point, you would just be computing for kind of a large complexity length. You're just computing at most 10 to the 4th values, because it would go from that value to the next 10 to the 4th, some range between there. So that could, in theory, lower your kind of worst case, where your worst case is based on complexity length being up to the full 10 to the 5th. I don't know. Is there any other approaches to simplifying the calculation here? I mean, I wonder if I can, really does, like the optimization I'm thinking of, really does kind of want to know the distribution of complexity length, like which factorial calculations are most common. Like if it's all kind of clustered in the 10 to the 2nd range, then you would want to pre-compute that array of 10 to the 2nd values in the hundreds, and wouldn't much affect things if you pre-compute the thousands. I guess another idea would be to pre-compute like 1 through 10 factorial 10, like the ones, the tens, the hundreds, the thousands, 10,000s. I guess that'd be like 10 values, or no, 10 times 4. So that'd be 40 values that you pre-compute. That should lower the expected calculation by a factor of 10. I don't know if there's a better way though. Maybe I'm just missing something. Okay, I'm going to try to do that. So 1 through 10, 10 through 10s, 10, 20, 30 through 90, hundreds, 100, 200, 300, 400 through 1,000, 1,000, so 9,000. So I think maybe how would I do this? Let's say I have a pre-compute array. And I think I want to restart this from 1 to n. N is 10 to the 5th plus 1. And let's say I have a index that I'm dealing with. There's probably better logic, but I just want to do this. I just want to do something that's straightforward seeming. So the pre-compute will have the actual factorial mod values, and the index is just going to be like 1, 2, 3, 4, 5. So I think if I have something where, let's say I have a base value or the place value. Let's say the place value is currently 1. And maybe I have a counter. I think it's going to be like 10 place values each time. 9 place values each time. 1, 2, 3, 1, 2, 3, 4, 5, 6, 8, 9, 10 through 90. So maybe the counter is up to 9. So let's say the counter is 1. I think that makes sense in my mind. Okay, so I can say here answer what is the logic here? If the answer mod the place is equal to 1, so the place value is 10 and the answer is 20. No, if the index I. If I mod the place is equal to 0, then pre-compute answers is going to append, and the index would be appended to I will be into the index. The count of things increases by 1. Maybe the count of things starts with 0. 1, 2, 3, 4, 5, 6, 8, 9. Count of things increases. 1, 2, 3, 4, 6, 8, 9. When I get to 10 is when I change places. The place will increase by something like if count mod something like if count mod 9, then place times equals 10. Okay, so it's something like 1, 2, 3, 4, 5, 6, 7, 8, 9. And then those are all going to have place value 1, 10, 20, 30, 40, 50, 60, 70, 80, 90. Those have all place values 10. Yeah, it needs to be 10. So I think count is yeah, it should be 10. So I want to go to when 10 is added to the thing, 10 is added to the index array, then it's gonna 10 is added to the index array. It's gonna change the place value to be 10. And this is 10, and then up to 100 is gonna be that. I think that's fine. And then okay, I think I just want to see what happens here. Print the pre-compute, print the index. Okay. Turn 0. Do 1 through 10, 10 through hundreds. Oh boy, this is not right. I don't want 110. I want this should be 100, and then this should go to 200. So this is 10. Let's count the 10. 11, 12, 13, 14, 15, 16, 17, 18, 19. So it's off by 1 consistently. So I think maybe I need to somehow work in a -1. If count mod 10 -1, count -1 mod 10. Say if really should be 10. If I do count -1 mod 10, that probably screws up. When count is 1. Maybe can I do this in reverse order? Count +1. That work? Almost certainly doesn't work. So if I treat this as count +1 mod 10, treat this as the original, maybe count +1 mod 10, where I do it before. Well, count +1 mod 10, that's just reversing the one I actually. Yeah. Uh, 9. Okay, 1 through 9, 10, 10 through 100, 100 to 1,000. Oh, shucks. Now it's 1,011. 1100. Probably keeps on screwing up. So how many values are here? There's 9 values here. 10 through 90 is 9 values. 100 through 900 is 9 values. Maybe I am supposed to be doing 9 values. Yeah, maybe I am doing 9 values, to be honest. How does that work? There's no way. No, this is 10 values. What am I thinking? No, it's 9 values. How is there only 9 values each time like that? Yeah. 1, 2, 3, 4, 6, 8, 9. Okay. Count mod 9 is equal to 0. One through 9, 10 through 90, 100 through 900, 1000 through 9000, 10,000 to 90,000, 100,000. Okay. So copy this pre-compute. And let me go ahead and comment this out. Okay, so the pre-compute is that. Maybe I'll move this around. Index, place, count. I guess instead of using count, I can just use length, right? The length of the number of indices. Yeah, I think that probably is correct. Okay. So here, this should be a simpler complexity calculation, or the answer calculation, because I can start with the lowest, with the thing nearest to that. I think I need the index still. So this is pre-indices, pre-compute indices. Okay, so does the impossible check. And then it does, I'll say the nearest is the index finding n within the pre-computed indices. So nearest is is going to be bisect left of the pre-computed indices, finding the value that is n. So if let's say n is 34, it's going to try to find 34 within this thing. And I'll find it at this index here. Index, this index where 34 would be inserted. So what I want to do is I want to use the pre-computed for one less than it. I guess if it's matching the value itself, what happens? So if it's 40, then it finds this index. Do I want to use bisect right? Because I don't want to insert it before the actual value. I think I want to use bisect right. So if it's 30, then it would find this index just like it's searching for 34. Then I want to use the one less than that index, so nearest minus 1, and use the pre-computed value for nearest minus 1. Yeah. So answer is going to be equal, starting answer is going to be pre-computed nearest minus 1, and going from every index in range of pre-computed indices at nearest minus 1. Okay, let's say I do start index is going to be by pre-computed indices at nearest minus 1. Answer is pre-computed at the start index. And for every index from start index to n, then I'm going to do the same complexity calculation. So this should be, no, I think I may have deleted it. This should just be answer equals answer times, should be index plus 1, start index plus 1. Answer times equal times index mod, and then return answer. Okay, let's see if that works. Oh boy, did that not work. Alright, simple test case here. Output is 24. That's a big number. Did say n was the length of complexity. Let's go ahead and just print out some stuff here. Do-do-do-do. 333. So the length here is 3. Oh yeah, this should have been n minus 1. I want to find n minus 1 factorial. Oh, oh boy. Okay. 232. So nearest. So n is 3. So I want to find 2 factorial. So 2 factorial should be 2. Start index should be so it's going to give me nearest should be index 2. So start index should be 2 minus 1, which is 1. So pre-computed indices should have started with 2. Yeah, 2. Or pre-computed at index 1 should be 2. So then it goes from 2. Fuck. This should be going from start index plus 1 to n minus 1. Still off. Start index plus 1. Is that right? So start index was 1. No, start index should have been 2. So range is from 3 to n minus 1. So 3 to 2. Okay, let's start. The initial answer was 6 already, so it's already trash at the start. So I'm thinking about indexing the wrong spot. Okay, so nearest returned 2. Which is the index of this thing right here, which is what I wanted. N currently is 3, right? So I want 2 factorial. Start index should be 2, because it's going to be pre-computed at index. Yeah, it should be 2. And the answer should be answer should be 2, no? Pre-computed start index. Should this be pre-computed at nearest minus 1 to match? Yeah. Oh, what am I doing? Why did that take me so long? Okay, so removing the printout, see how this compares. Okay, not add, mod. Oh, did I delete it? Oh. I guess maybe I should have declared it at the very front. How do I want to do this? Should just probably have something here. Just to make this code correct if I uncomment it for some reason. Okay, this is all fine, I think. Jeez Louise. Very odd. This isn't even that long of a string. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 values. Okay. So we should be doing like from 10 onwards. Should be doing from 10 onwards. 10, 11, 12, 13. Oh boy. One, two. I think this is. Unless these values are just straight up wrong. So I'm expecting here it should be like 11, 12, 13 is being printed out. What the hell? Just 11? So, sorry. So it should be, if there's 13 values, then it should be multiplying 11 and 12. N is 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it should be doing 12 factorial. If it's doing 12 factorial, then it should be doing. Shouldn't it just be like that? Oh, okay. Guess I had it right the first time, but all the test cases were below length 10. So I wasn't really testing whether or not n versus n minus 1 was working. I just assumed that that change worked. Okay. Well. Okay. I mean, how do I feel about this? I don't feel great about this. There might have been a better way of handling all this. Okay, but this is basically, in the end, a way to do faster factorial with some sort of pre-computation. I guess in theory it worked out. I guess it is good in the sense that my theory about how to make this pre-computation faster with these sorts of indices, kind of logarithmic indices, pre-computed, would speed up the overall calculation. Alright, let's go to summary. So basically simplified formulation of the math involved is doesn't work. No sequence possible. If any value after the start is smaller than starting value and start value. So if it has a smaller than or equal to. So if it starts with a 1 and then goes down, or starts with a 5 and goes down to 4, 3, 5 to 2, 5 to 1, that doesn't work, because then you'd never be able to unlock that lower value. Value computer. And then all other cases, any possible permutation will work. The answer is equal to n minus 1 factorial. Because you can always use the starting, since j can always be equal to 0 and j is less than I. Right. So anyways, in summary, need to calculate or return factorial of n minus 1 or n minus 1 factorial, where n is the length of complexity array. So can do this kind of slowerly, additive is slower. Can do this using factorial and mod, but since the size of n can be large, in this case 10 to the 5th, those values can be very big and make it slow. Optimization above is to pre-compute certain values of n and their factorial values. Pre-compute certain factorial values of n. Pre-compute factorial of n for certain values of n. Consider the space of inputs where n goes from, where 1 is less than or equal to, n is less than or equal to 10 to the 5th. Which values of n would make it fastest, would make return fastest. So here use logarithmic spacing for values of n computed. So i.e. 1 through 9, 10 through 90 by tens, 100 through 900 by hundreds. A 1,000 to 9,000 by thousands, etc. Since that guarantees a factor of 10 decrease for calculating any arbitrary n value to its closest pre-computed value. So for example, if let's say n is equal to 85, use pre-computed value for 80 and multiply, for 80, 81, 82, 83, 84. So instead of going multiplying 1 through 84, you're just multiplying 80, which you already get from the pre-computed, with 81, 82, 83, 84. Okay, then above pre-computes those values and uses them to simplify the calculation. Okay, and obviously that's easier to describe than to code, given how long it took me to code this shit. Yeah. Keeping track of the pre-computed values, the indices that are associated with it, then on the actual code, finding the thing that you want to find the value you want to take the factorial of, getting the index, getting the pre-computed value, and then moving from there to get the answer. Alright, time complexity, this can be O of n to pre-compute, to pre-compute the values, O of log n after for using pre-computed values in order to iterate from closest pre-compute to actual n. And then space complexity, this can be O of log, is it O of log n? Yeah, I guess so. Yeah, O of log n to store pre-computed values. There's one thing here. Oh yeah, you do need to search, but the search is very fast. It'd be n log n. No, it'd be log n, where n is actually the length of the pre-computed stuff, which is already log n. So that'd be searching is going to be log n. So yeah, so that's not really part of the overall calculation for time complexity.